And so in chapter one, we handled first order. Chapter one, we handled first ordered. They weren't systems at that point. Sorry, first order problems. Using three techniques: analytical techniques, qualitative techniques, and numerical techniques. So now we're going to start modeling a system. We're going to start with some qualitative techniques. So qualitative doesn't always mean graphing it. Sometimes it means just finding out information, right? Um, and so let's start with a simple system. So the population of rabbits and population of foxes. So imagine you have some island, right? And you have some rabbits on it, and you have some foxes on it, right? And so, and let's pretend you have an infinite amount of grass, right? That way the rabbits can eat whatever they want. And so basically, let's look at the system and let's kind of break it down for a second before we get into any of this. So look at the system and make some core observations and then find this. So let's look at this system. So notice here, if we start with no foxes, if there are no foxes, let's pretend there's no foxes for a second, right? If there are no foxes, aka f equals 0, right? If there's no foxes, what happens to the rabbit population? Well, this becomes 0, right? So the rabbits here will, you know, grow without limit, right? So if there are no foxes here, the rabbits are going to grow without limit. In fact, we could figure out what the answer is here, right? Here, what's the answer to the rabbits? Rabbits equal whatever my initial rabbit population was, right? E to the 2t. I mean, that's the solution here, right? So I get infinite rabbits. Rabbits will do what the rabbits do, right? And notice here, if I have no foxes, um, hold on, I'm writing on the wrong layer. Let me go back. Let me go back. Fine, be that way. That's too far back. Notice here that here if I have no foxes, DDF is always just going to be 0, and I start at 0, so I'm going to stay at 0. So here, f of t is 0, right? And that makes a lot of sense. If I don't have any foxes, foxes aren't magically going to appear, right? They just don't all of a sudden appear out of nowhere, right? And my rabbit population grows up. This. What happens is if I have no rabbits, right? So I have no bunnies. Now, does this kind of exist in real life? Is there any place where there's rabbits without predators?
Golf courses.
My house. Hold on, let me see if I can find it. My backyard. Hold on, let me see if I can find it real quick. Yeah,
There are
hold.
like billions of them on some golf courses.
Um, yeah, but there are predators because there are coyotes around here.
Not enough.
Not enough.
It's the exponential wave of bunnies. There's no end.
So let me see if I can find this.
So are we conspiring to like destroy bunnies? Because this could be
Oh,
fun. I'm sure we could find out exactly how many foxes we need to start like mass producing.
all right. So in Okinawa is also known as Rabbit Island, right? And so here's an island that's kind of off the coast of anyone, right? And so what happened was is somebody um, has a huge rabbit population because someone just let a bunch of bunnies, those pet bunnies, loose there, right? And there was no predators. So guess what? There's just bunnies form the island, right? And so it does happen, right? And where things can happen. So this is not totally a farce. And in Yellowstone, they killed off, or was it Yellowstone?
It's Yellowstone, yeah. You're talking about the wolves?
Yeah, they killed off all the wolves.
Yeah.
And then all of a sudden it's like, oh, it's bad. And then they introduced back the wolves, and all of a sudden all the species started doing a lot better. It's like, maybe we shouldn't mess with things. So it happens. So let's pretend we have no rabbits, right? If we have no rabbits, our rabbits stay 0, right? So the rabbit population stays 0 because I have R and R would be 0. So the rabbit population stays 0. What happens to our foxes here? Our foxes, here we have our fox naught, whatever our initial amount of foxes is, equals to just minus t, right? Because this part is 0. And so our foxes just seem to decline and die. And so it's important to be able to look at an equation and ask some of these questions. What happens if one is 0? What happens if the other is 0? Does that make sense? Does this system make sense of what I'm trying to do? And so what do we have here? So what do some of the other terms mean? So this means just bunnies will populate, right? If in absence of predators. And what does this term mean, right? This term means RF. What does this term mean? It's the rabbits eating the foxes, right? It's my dyslexia. In this backward world, rabbits eat foxes. It's the foxes eating the rabbits. It's like, Professor Meager, I don't know what world you live in, man. Be one of those rabbits from like Five Nights at Freddy's or something, just showing around, right? I've never played that. And so here, this is the rabbits eating the foxes, and this is just them reproducing with infinite supply. What does this mean? This means that foxes are dying off, right? So the minus f is just foxes dying, right? Foxes dying off, foxes dying off. And this plus 0.9 RF is the foxes eating the rabbits. So it's the same here before, but this time foxes eating the rabbits. Allowing them to have kits. Kits? Is that right? Kits is the baby fox. Is it kits or kids? I don't remember. This is why I don't teach elementary school. I don't know it. I'll look it up.
They are called pups. I guess that makes sense since they're canines.
They're just called pups?
Just pups.
Oh, okay.
Oh, lupine, not canine, same thing. Basically dogs.
Yeah. Just considered pups. Depends on what culture. So technically it's a kit. Kit's the old word for it, but now we're just use pups apparently according to this website. Who knows?
Foxes are canines.
Yes. So okay, so we kind of get this. So how does, if I wanted to find an equilibrium solution, how would I go about doing that? So let's find the equilibrium solution real quick. How would I find that? What did we do last time? We said our equilibrium solution is where our change is 0, right? That means I've hit equilibrium, right? At least in static equilibrium. You can have something called dynamic equilibrium. We'll look at that in a second. So here I have 0 equals 2r minus 1.rf. And then here we have 0 equal to minus f. So let's find the EQ solutions. Equilibrium. I call them equal solutions. I don't know why. I've just done it for years, I suppose. But now that I write it, I'm like, well, why do you do that? Do you guys know what jamais vu means? It's the opposite of deja vu. Jamais vu is the sensation that you've never done something, though you know you've done it 1,000 times. It's the opposite of deja vu. So deja vu is you're doing something you know you've never done, but it feels super familiar. Jamais vu is you're doing something you know you've done 1,000 times, but you're like, this is all new to me. I don't know if you guys experience that daily. Oh, good. Now you have a name for it. Jamais vu, which means never seen in French. Anyways, so how do we do this? How would I solve this? Well, the answer here is just solve one for. We'll, yeah. Here we just factor this out. So here we're just going to factor out an r. So I have r equals 2 minus 1.5f. And so in order to solve for a system of this is nonlinear, right? So we can't just chuck it through an argument matrix. And so when it's nonlinear, what you do is you factor out the best you can. So this is 0. So that means either this is 0 or this is 0. If r is equal to 0, or it means that 0 equals 1.2f, or f is equal to 2 divided by 1.2. So roughly 1.67. So here, if this is 0, that means r is 0. If this is 0, that means f was equal to roughly 1.67. Okay. Then we're going to plug that into this equation. So here I have, and I'm going to do the first one. So here I'll have r equal to 0. So this will be minus f plus 0.9 r. But in this case, we're going to plug in a 0. F. And this point, this is 0. So this is 0. So I have f is equal to 0. And so I have the equilibrium point 0, 0. Here, I'm also, if I plug in 1.67, so here if I have 0, this is equal to, if I plug this in, this is 0 minus 1. I'll just put it in correctly, and then I'll simplify later, plus 0.9 r, r 2 over 1.2. Oops. And then here, if I solve for r, hold on, r is equal to 1 over 0.9, so approximately equal to, well, actually I can write this is equal to 1.1 repeated. Okay, and so here I have another point of 1.1 repeated and 1.97. And so here I have two equilibrium solutions. So how did I do this again? I took one of the equations, I set it equal to 0, and I solved for its cases. In this case, it's 0, r equals 0, or f equals 1.67, right? Then, if r equals 0, I plug that into the second equation, I get 0 and 0. If f equal to 1.67, I plug that in the second equation, I get 1.1 and 1.67. So let's actually look at this thing for a second. How do you tell which is the x and which is the y? I made that decision. I'm just going to say the rabbits is more independent in my opinion, because rabbits without foxes exist perpetually. So I say that's the more independent one. But that was just my preference. Just a preference of what I chose. All right, what am I looking for? I want the happy thing. All right, so in this little DE tool things, I asked you to download, or you can use other things, but I'm going to show you this one, just to show you something. We're going to have this thing called HGBT System Solver. Bing. And so here we're going to set X to be the rabbits and Y to be the foxes. So let's plug this happy puppy in. And I want to show you what this looks like. All right, so I'm not in any rush to do this. In a sense to get you guys lost. In fact, I specifically gave me an extra week just in case I wanted it. Times X times Y. Hi, it's the wrong button. Because I do not want to just chuck you through the first part and get you horribly lost of what we're doing. Because eventually we all end up in higher end math classes where you're just making alphabet soup. And what do I mean by that? I mean by you're just doing a lot of math. You can crunch through the numbers, but you have no clue what's going on. You just halfway crunching numbers. Ah, these are answers, right? If you haven't been there yet, you will be there soon. All right, so let's go ahead and look at this. All right, now does it make sense to have negative rabbits? No, that makes 0 sense. So it doesn't make sense to have negative rabbits. Does it make sense to make negative foxes? No, that doesn't make sense either. So here we are. So I'm going to have this thing look like this. And so let me quickly explain what this is before we actually do it. So here, these little arrows, let's see if I can slow this down. So these little arrows, so basically at any point x and y, I can figure out what my derivative is, right? It's going to be, so if I give you 5 and, or in this case, like, let's just say I have 2.3 rabbits and about 0.9 foxes, I can figure out what my rate of change for my rabbits are and the rate of change for my foxes, and I can move a tiny little step. And then I can move a tiny little step and move a tiny little step and move around, right? And so what it does is I'm creating just kind of what a solution will do in time, right? And so here I've really slowed it down. Maybe not as much as I wanted to. Clear. I want to go a little slower. A little slower. Let's do, there we go. And so what it's going to do is it's slowly going to go around and move this. And so this is what's going to happen with my rabbit and fox population. So this is my, here's the X is the rabbit population. So the rabbits come up, they get eaten by the foxes. The foxes, the more and more foxes come, right? They ate all the rabbits, and the foxes ate all the rabbits, and all of a sudden they start dying off. So the foxes start dying off. There's less and less foxes, so the rabbits can reproduce. So the rabbits reproduce. There's a lot of rabbits, and so the foxes start eating them. And notice how this here. And we would call this, in my opinion, dynamic equilibrium, right? Because here it is in some sort of equilibrium, right? But it's not all that flat. Well, let's test our solution. What was our solution? 1.67 and then 1.11 foxes, right? So let's test the solution. Boop. And notice here, there's a tiny little dot there. I don't think you can see it. It's a tiny little dot there. And notice if I have this exact number, the foxes and rabbits are in perfect equilibrium, right? I'm going to clear it and have the solution, right? They're in perfect equilibrium, okay? They're not moving, right? Now, this is assuming that foxes and rabbits don't have any gestation period and they just instantly just produce rabbits and foxes and eat rabbits and foxes instantly, right? That's not all that real. Where's the other solution? Well, the other solution is at 0 and 0. That makes a lot of sense, right? Because here I have a successfully modeled the rabbit and fox population on the moon. There's 0 rabbits, 0 foxes, and they stay that way, right? And so we're going to get used to systems of equations. And so and the reason I want to get the systems of differential equations is because out in the real world, nothing works in isolation, right? And so you're going to have to learn how simple alterations affect things and do things. All right, so we've done this. So this and that's that. All right, so let me go ahead and export this real quick. File export. The way I'm going to do notes for videos for this section is just every day is going to be a video. Okay, so if it takes us 5 days, it'll be 5 videos. And I'll try to end on a page number. All right, so let's do this. Get rid of this. Yep, don't save. All right, so let's look at this. Now let's change this up a little bit. What have I done here? All right, so what have I changed here? So let's look at this in what have I changed? What are the equilibrium solutions? I have added this. And does anyone have a clue what this is going to do? Anyone have a guess? What is this going to do to the rabbit population? Let's assume no foxes for a second. What's this going to do to the rabbit population by introducing this 1 minus r over 2? It will reduce them, right? But let's pretend I start with 0.5 rabbits. What's going to happen? Anyone have a guess? If I start at 0.5 rabbits, this is going to be positive, this is going to be positive, right? And so I'm going to increase my rabbits until I have rabbits of what? 2. Once my rabbits are 2 population or 2,000, whatever units I'm using for my rabbits, right? This will 0 out and be flat. Let's pretend I start with 10 rabbits, right? Or 10,000 rabbits, whatever my R unit is, right? This will be negative and this will be positive. And so this will slowly go down to when I hit 2. And so this is kind of like a population cap, right? And this is what really happens out there in the real world. There's a population cap. And so on the Rabbit Island where there are no foxes, there's a population cap. The grass grows at such a length, and or the humans feed them. Because let's face it, people show up on boats with a bunch of rabbit pelts and chuck them all over their bodies and have billions of bunnies on their head, right? Nothing says Easter like being covered in bunnies, right? So it's a limit food supply type thing. And so this limits the rabbits. And so this changes the system. And so let's find the equilibrium solutions and see how this looks. So here we're going to find the equilibrium solutions again. So here I have 2r of 1 minus r over 2 minus 1.2 rf. And then I have 0 equals. So this is the exact same. So let's see how it affects. So we're going to do a tiny little change and see how it affects everything. Do a tiny little change and see how it affects everything. So, where am I at? Okay, so we're going to find the equilibrium point. So here, let's do this. Let's see if I can solve this through. So here I have, let me check the r. Let me check the 2r through. So here I'll have 2r minus r squared minus 1.2 r. Yeah. All right. So here we're just going to factor out the r. In fact, I think, hold on. Honestly, I think it's better to use this one first, right? And why is that? Because I don't have to deal with this mess, right? I don't have to deal with this mess. And so here, if I do that, I get 0.9 f. Let me just factor out the f. So I'll have f or negative 1 plus 0.9 r f or r. So that means either f is equal to 0 or r was equal to 1.11 or 1 repeated, right? You check this through the other equation. So if f equals 0, r equals 0. So let's just do that real quick. So here I have 2r minus 1 minus r over 2 equal to 0. That means we have two solutions here. Let me make sure that's clear. And then here, so either r equals 2 or r equals 0 or r equal to 2. Okay. And so I make clear point 0, 0, 0, 2. And then here, the other equilibrium points, if I have r equal to 1.7, so 0 equals to 2 of 1.1 repeated, divided by 1 minus 1.1 repeated over 2 minus 1 times 1.1 repeated times f. You solve for f, you're going to get f equal to be 0.74, roughly. And so we have the 1.11. Oops. And then we have the 0.74. Okay. So let's look at this. Let's look at this again on our little happy system. All right, so now I'm going to introduce my limiting factor, my population cap here. So it'll be 1 over x divided by 2. Woohoo! So let's look. Woohoo! Thank you. Why are you grumping about me now? Unknown identifier? Oh, hi. All right, so let's plug in our equilibrium solution 0, 0. Yep. I've successfully, again, done the rabbits in the middle of the moon. Let's pretend we have 2 rabbits. Let's clear this away. Once again, I have successfully, here, if I start through at population cap, I'm going to stay at population cap. And let's do the other one. If I have 1.1 and then 0.74, look at that solution. And then here I have the equilibrium. Is it 747? And so it moves tiny a little bit since my numbers aren't perfect, right? Okay. And so here we have our three equilibrium solution. But let's look at real quick what happens right here. Notice here if I start, let's say if I start with 5 rabbits, what happens to our solution? My rabbit population just seems to collapse to its holding capacity. And if I start with less than that, 0.5, my rabbit population just seems to crash into that. Now, but here's something interesting. Let's pretend I start anywhere else. Anywhere else. Hold on, let me clear it. And notice what happens here. Just by introducing this one little term, I now have a completely different system. Because this system, instead of just going around and around in some equilibrium, just crashes into an equilibrium point. It just kind of goes that. It doesn't matter where I start. It's just going to go to that point. And I can start way over here. And it will go to that point. And so here, even that little bit of change, right? Even that tiny little bit of change changes how the system acts in a global's perspective, right? Because now it always is going to crash into that point, which is good to know. Because here, if I start with any number of foxes and rabbits, it doesn't matter what, right? I can have 2 foxes, assuming that we at least have 1 male and 1 female fox, right? And some number of rabbits, I know what I'll have long term if I just by introducing this tiny little cap. Okay. So, yeah. So let me do one more thing with you for the equilibrium solution. So I want you to get used to finding equilibrium solutions. So here's something that's a little bit more complex, right? And so it's the same thing as how to find equilibrium solutions. So let's look at this. So here we have some equilibrium, a system of equation, nonlinear, right? This is nonlinear, this is nonlinear. The whole thing's nonlinear in a horrible sort of way. So the first thing we want to do is set both equal to 0. So we set it equal to 0. So we have 0 equals 2x, 1 minus x over 2 minus xy. All right. So we set it equal to 0. So we're going to pick one of them. I'm going to take this one, right? I'm going to factor and solve. And so I can't really pull out too much, but I can pull out at least an x, right? So here I'll have an x, and then this will become 2 minus x minus y. See how I can show. So I moved the 2x in here. This 2 cancels this 2. Oops, I'm writing on the wrong layer. This 2 cancels this 2, so I have this. So that means either x is equal to 0 or this mess is equal to 0. Now, does this mess equal to 0 really help us right now? Not quite yet, right? But we'll go ahead and keep it. So that's what our 0 multiplication rule gives us. All right, so let's go ahead and do this. And I'm going to go ahead and I'm going to simplify this one just for my own sanity. So here I'll have y, and then I'll have 1 minus y minus 2x. Okay. So I'm just simplifying this, aka I'm distributing the 3y. That's all. And then
should that be a y times parentheses 3 minus y minus 2x in that bottom row?
Yes. Thank you. So distribute the 3, distribute, and factor out the y. All right, so here, what do we have? So we have 0. All right. See how I can do this. I want to do this so I don't get you confused. All right, so let's do this. So here I have x equals 0. Let's look at this. I'm going to plug that into here. So if x is equal to 0, that means 0 equals y minus 3 minus y. Okay. And so what does that give us? That gives us either y is equal to 0 or y is equal to 3. And so that gives us two solutions, right? So we have the solution here of 0, 0. So x and 0 and y is 0, or the solution here of 0 and 3, where x is 0 and y is 3. All right, let's pretend this is 0. Now, does that help us? Does that help us? The answer is kind of yeah, because here I can solve it for x. If I solve this mess for x, what do I get? Well, here I move x over and I get x equals 2 minus y, right? And then I can plug it into here. And so here I have 0 equals y, 3 minus y minus 2 times 2 minus y, right? So everyone see what I did there? Any questions on how that went down? Okay. Now, so I eliminated a variable and plugged it in here. And so now this is only in y, so that means either y is equal to 0 or, hold on, let me do this real quick. This will be minus 4 minus to y equal to 0, or this is 0. And if this is 0, this is, hold on, I can do math. Hold on. Let me just do it slowly then if I can't seem to do it fast in my head. So y equals to 1. Okay, so y equals 1. And so if y equals 0, x equals 2, so I have 0, 2. Oops, all right, I like 2, 0. And then if y equals 1, x is equal to 1. And so here are my 4 equilibrium points. Okay, so it makes sense how to crunch through that. So if I ask you what equilibrium point for a system, even if it's none, this is what you do. You set it equal to 0. You find the zeros for one of them, and then you plug those zeros into the other because they both have to be 0 simultaneously. Okay, any questions on this? If not, we're going to move on to the next page. All right, so let's go ahead and export as PNG. Let's see. All right, let's look at this. All right, so let's start putting stuff into vector notation. And so here, in order to solve a system, we're going to put stuff into vector notation where we're going to have a vector equal a vector. And so in order to do this, we're going to kind of write this as, I'm going to call this my population vector with respect to t. And the population vector with respect to t is going to be equal to r of t, f of t. So here we're going to have that. And so we can write dp dt. And so here we're going to take a derivative of a vector. In order to do that, you just plug in the derivative for each of its components. So this will be dr dt plus df dt. So you just kind of stuff it in. This is equal to the vector of 2r minus 1.1 rf over minus f And so now I've written this as a vector. So my population vector, which is the rabbits over foxes, right? So rabbits is my first insert, my foxes over. And the reason we're going to start doing this is we're going to start putting it into matrices and we're going to start solving for eigenvalues and eigenvectors and do all that stuff. But before we get to that, let's introduce the notation. All right, so after solving a system of ODEs in vector form, we can assign a vector and draw it at the location. So at every vector, at every point on for any point at any point time, I'm at r, whatever r or f of t is, right? I may not know what that is, but I can know what direction I'm going. Okay, if I solve this vector right here, it's going to point, that vector will point in the direction in which the solution will go. Because if I have positive amount of rabbits, it's going to point up, right? If I have a negative amount of rabbits, a negative change in rabbits, it's going to point down. The rabbit population is going to go down, or it's going to go up. Oh, I'm sorry, I lied. Whoop. All right, go back. If I'm talking about rabbits, rabbits is what? Our x-coordinate, right? If I have a positive amount of rabbits, it's going to point to the left. If I have a negative amount of rabbits, it's going to point to the right. If I have a positive amount of foxes, it's going to point up. If I have a negative amount of change of foxes, it's going to point down. So here, if I have some point of change, that means I'm going to increase both in rabbits and in foxes, right? Here means I'm going to increase in rabbits, but decrease in foxes. And so here, the way the vector point kind of tells you where the solution is, very much like what we've seen here, right? It's going to tell you which way the solution is going. And here, let's clear this and watch this a little bit slower. So notice here, if I start here, let's go ahead and stop for a second. So what happens here? Here, I'm going to be decreasing the amount of rabbits I have, right? Because here I'm showing decrease in rabbits, since my rabbit population is going down. But here I'm going to increase, because I'm slightly pointing up, my fox population goes up until this point. And so that's here. Then I'm going to start decreasing my both of them. And so these both go down. So notice how these are both going down right here. And then here I curve around, and then this is going to start. So here my rabbit population is going up while my fox population is going down. So right here in this curve, and then it comes up. And so this is what we're going to do. So this is how we make this. And so we can draw a vector at each point. We're going to normalize these vectors, and we're going to call that a direction field. So a vector field is nothing's normalized, and so the vector strength will be really, really strong. But most of the time you just do this. And once we draw all this together, we call this the phase portrait. Once you've drawn a couple sample solution, we call this the phase portrait. And so the phase portrait is either a vector field or direction field with a couple sample solutions on it. Okay, so how do we do this? I'll show you how we do it by hand, and then maybe what the computer's doing will make a little more sense. So let's do this by hand. So let's pretend we have some vector. And here, let's pretend I insert the point 0, 0. So 0, 0, right? So let's call my v vector x and y, just real quick. So let's plug in 0, 0. Let's plug this vector in. Yeah. So ddt of, how do I want to show this without making it seem weird? Let's just plug in some values. Let's plug in the value 0, 0. That means dv dt for this will be 0, 0. Because here I have 0 here and 0 here. And if I plug in 1, 2, dv dt of this would be 1 and 2, just because this produces the same thing. So here at the origin, I have a 0 vector. It doesn't really go anywhere. Here at 1, 1, I have a vector length 1 going that way. Here at 0, 1, I have a unit vector going this way. In fact, let me use a different color so you can see it a little bit better as I draw them in. And so here at -1, -1, I have my vectors this way. At -1, 0, it's this. And so here, does everyone see how this is producing a field? I'm just plugging in the values of my given values and making a vector. It's all the same. Any questions on that? Let me scroll up just a bit. So here at 1, comma 2. So here if I'm at 1 over and 2 up, so 1, 2 up, right? So I start here, and then my length in the x direction is 1, but my length in the y direction is 2. So it looks like this, and so it gets a little bit stronger. And notice here if I was at 2, 2, this would be a lot stronger here. And if I was at way over here, it'd be way like, oops, here, it'd be very much like this. And so here, just kind of, vectors get larger and larger and larger. Let's do something a little bit less trivial for a second. So let's look at this. Let's just put in a couple points. So here, let's pretend I'm at 1 and 1. If I was at 1 and 1, my x direction would be -1, and my y direction would be -2. So I'd be very, very strongly this way. Oops, let me do this in blue again. So I'd be very strongly this way. And here, if I'm at 2, 2, it'd be very strongly in the same direction. Here at 1, 2, it'd be almost like this. So this all kind of points in. But it points in with a heavy slide. And let me, instead of doing this by hand, that's why we have computers, let me show it to you in the computer. Where's me Java? All right, so let's get rid of our fancy one. And let's put in these 2 simpler ones. So you only need to show just 1 or 2 on the notes. So here we have x and y. Okay. And so this one, oops, let's go ahead and do from -4 to 4. Let's assume that it makes sense to have negative things again. So here, this one just kind of goes out, this one kind of goes out, this one kind of goes out, right? So this is what the phase porch would look like. Here, if we did it the opposite, so -x, let's do the other one, -2y. No, I know. I don't know what 2y is. I have to be very specific with you. It's fine. It's a nice program. It's just you have to be very proud. And so this is what it looks like here. And so here, notice here that the y term goes to 0 a lot faster than the x term. And so here, and then here, if I just put a couple of these in, this is what we consider the phase portrait when it has a couple drawn in. Okay. And so this is how these are created. Let's do one last one. I guess it's the end of the day. We'll only do 3 pages today. We did a lot of preamble.